Hello friends, welcome to today's lecture Stiffness Matrix Method. Myself Mr. Y. S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yatra. In the last lecture, we discuss or we solve a problem by using stiffness method. In this lecture, we solve a problem that is sinking of support. Let us see. Analysis of beam with sinking of support. Sinking of support means what? The support is settled by somewhat distance, and due to that settlement, what are the moments occurred in the beam, and due to that moments, what are the external that fixed end moments generated, we need to calculate it. Let us see. Analysis of continuous beam as shown in figure using stiffness matrix method. If the support B is sinks by 10 mm, take the flexural rigidity EI is 6000 kilonewton meter square. So this is a beam A, B, C, D. A is a fixed end, D is also fixed end, and B and C is a roller support. And at point B, it sinks by 10 mm. Sinks means it is a settle down by 10 mm. So first we need to calculate fixed end moments. Due to sinking of support B, fixed end moments will be developed in the member AB and BC because the B is a in between AB and BC. So due to sinking of B, the moments are generated in between span AB and BC. So we need to calculate moment at AB and BC. So this is a first AB portion that sinking by 10 mm, and for that sinking the fixed end moments is the moment is generated, that is anti-clockwise at point B and anti-clockwise at point A. So due to that sinking of support, what are the moments are generated is MFAB is equal to MFBA is equal to minus because due to that anti-clockwise moment, that is minus 6 EI delta upon L square. So C and moment of inertia for this AB is 2I, and for that BC is 2.5 and CD is a 2.5. Span is 3 meter, 4 meter and 4 meter. So minus 6 into EI is already given, that is 6000 kilonewton meter square, into I, that is into 10 mm, that is converted into mm, is 0.01. So divided by L square, that is 3 square. So it becomes minus 12 into 6000 into 0.01 divided by 9 is minus 80 kilonewton meter. This is a fixed end moment at AB and BA, and both are anti-clockwise. Then next, similar way, calculate fixed end moment for BC and CB. So due to this sinking of support 10 mm at point B in between BC span, the moment is clockwise at point B and clockwise at point C. So it consider plus, that is 6 EI delta upon L square. The EI becomes now 2.5. So 6 into E into 2.5 I into 0.01 divided by 4 square, and EI is given, that is 6000 kilonewton meter square. So 15 into 6000 into 0.01 divided by 4 square, that is plus 56.25 kilonewton meter. This moment only produced between AB and BC span. There is no sinking at point C and D, so there is no movement between MFCD and MFDC, so it becomes 0. Only moments produced between AB and BC span. So displacement matrix, form a displacement matrix. Degree of kinematic indeterminacy for this case is 2, that is theta B and theta C. So hence displacement matrix becomes theta D matrix is equal to theta B and theta C. Then next, matrix of action due to loads. So since unknown displacements at point B and C, so we need to calculate moments, fixed end moments at point B and point C. So first is ADL1 is equal to MBA plus MBC, and MBA value is minus 80 kilonewton meter plus MBC is a plus 56.25 kilonewton meter. So consider with sign calculations. So ADL1 becomes 23.75 kilonewton meter. Then ADL2 is MCB plus MCD. So MCB is plus 56.25 and MCD is a zero value. So it becomes plus 56.25 kilonewton meter. So ADL matrix becomes minus 23.75 and plus 56.25. This is the ADL matrix. Then next we need to form a stiffness matrix. First column of the stiffness matrix, and we know the unknown is the B and C. So apply unit displacement at point B. So first is S11, that is S11 is for that AB and for that BC portion. So force is that is 4 EI upon L. So 4 into E, the moment of inertia for this AB portion is 2I divided by L is a 3. So 4 EI E into 2I upon 3 plus for this BC portion is 4E into moment of inertia for this BC is 2.5I and span is a 4. So 4E into 2.5I divided by 4. So it becomes 5.167 EI. So this is a S11. Then next S21. So S21 becomes 2E into 2.5I upon 4 is equal to 1.25 EI. So form a second column of matrix. Apply unit deformation in the direction of theta C. This is the unit displacement, that is theta C. So S12 means unit displacement at point C. What is the effect on the at point B? So it becomes far end is a fixed. So it becomes 2E up EI upon 4. So I is a 2.5 I divided by span is a 4. So it becomes 1.25 EI. Then S22 at point C, consider this CB and this CD part. So 4E I is a 2.5 I divided by span is a 4 meter. So 4E into 2.5 I divided by 4 plus for this CD portion is same values, that is 4E into 2.5 I divided by 4. So it becomes 5 EI. So form a stiffness matrix, that is S matrix is equal to EI is a constant term, so take outside of the bracket. So 5.167, 1.25, 1.25 and 5. This is our stiffness matrix. Now to solve the stiffness equation, we know the stiffness equation is AD is equal to ADL plus S into D. AD matrix is a zero matrix, so it becomes 0 is equal to minus 23.75, 56.25 plus EI 5.167, 1.25, 1.25 and 5 and theta B and theta C. So the unknowns are 2, that is theta B and theta C. Form a 2 equation, that is theta B into 5.167 plus theta C into 1.25 minus 23.75 is equal to 0. Theta B into 1.25 plus theta C into 5 plus 56.25 is equal to 0. The unknowns are 2, that is theta B and theta C, and we know the two equations. By solving two equations we calculate theta B and theta C. So we get, after solving equation, theta B is equal to 7.79 upon EI and theta B is a theta C is a minus 13.198 upon EI. This is the solutions for this equation, that is theta B and theta C. Now by using this theta B and theta C value, calculate final end moments. So final end moments calculated such a way that MAB is equal to 2 EI upon L into 2 theta A plus theta B plus MFAB. Now we know the value of the theta A is 0 and theta B is 7.79. Put up theta A and theta B and MFAB is already calculated in the first step, that is fixed end moments. So solving this equation we get minus 69.613 kilonewton meter. Then similar way MBA is 4 EI upon L into 2 into 7.79 upon EI minus 80. So it becomes minus 59.227 kilonewton meter. So MBC is 2 EI upon L into 2 theta B plus theta C plus MF BC. So 5 by 4 into EI into 2 into 7.79 upon EI minus 13.198 upon EI plus 56.25. So it becomes 59.22 kilonewton meter. Similar way we calculate for MCB, the 2 EI upon L into 2 theta C plus theta B plus MF BC. In this equation we know the both values theta C and theta B. So put up this value in this equation and we got MCB is becomes 33.33 kilonewton meter. For that CD is 2 EI by L is theta C plus theta D. Now theta D is becomes 0 because there is a end is a fixed end. So MCD becomes minus 33 kilonewton meter. Then MDC is 2 EI upon L, that is 2 theta D plus theta C. Now theta D is 0, put up theta C value only and calculate MDC, that is minus 16.5 kilonewton meter. Now there is no load on the beam, so there is no free bending moment diagram. You just draw the directly fixed end by the final fixed end moments and plot first that at MA is a 16 minus 16 and minus sign plot upside of the baseline, positive sign plot bottom side of the baseline. So first is at A is a 69.613 minus, so plot upside. At B is a plus 59.227 plus, so plot bottom side of the baseline. At point C it becomes 33 kilonewton meter, so plot upside of the baseline. And D is a plus minus 16.5 kilonewton meter, so plot bottom side of the baseline and join all the points. Above the baseline this is a negative bending moment, below the baseline it is a positive bending moment. This is your final bending moment diagram, and this is the solution for a problem sinking of the supports by using stiffness method. Thank you.